I'm Dr. Christine Coe. I just started here in last fall, and we started a new project that is experimental aerosol atmospheric physics. And it was a stage 4, like 4 stages project that was funded by the Sonoma Waters. So it's an environmental project to detect air quality locally here in Sonoma County. And we started from zero, like a brand new lab with absolutely nothing, gathering all the materials. So our 2 students here, Angel and later that will follow up with Jack, did all the groundwork for this project. Really slide by slide is their hard, like sweats and tears in them. And they finished stage 1, and I'm very proud, and it's my pleasure to introduce Angel for doing all the late night work. And it came fruitful that we finished stage 1 ish, and that we have a working system, and that soon next year, probably moving on to our other students, maybe somewhere, that we will start the stage 2, and we'll have a final product. Before we move on, I just want to introduce the project in a broad spec. Is that not only, the purple air sensors, everyone, right, that you go into the wildfire, which season already started, right, and it tells you how many bad particles are in the air. Don't go outside. However, we don't know the detailed information in them because it doesn't tell you, oh, there's actually more bacteria in there, or there's other dangerous things in the air to breathe, such as in this room, you have no idea what's in the air, right? So we were actually thinking of bringing the cart. However, we didn't want to, waste more time or have a red light going off and everyone doesn't want to be here. So yes, so those kind of projects were our 2 students were working on. And I'll give it to Angel.
All right. Hello everyone, my project is on creating a mobile dynamic light scattering. My name is Angel Corletto, and my capstone professor was Dr. Coe, and this was for Physics 491. So, what's the project? Well, it's to detect particles that are in the air, just like what Dr. Coe just said. It's just to see what exactly is in the air, what are we breathing. Our goal is to create a portable air quality measurement with more information than a traditional DLS setup that's more expensive. In the picture to the right, you see, it's a little cut off here, but this is like a traditional DLS setup, and it will cost you not too expensive, but about $30,000. If I had that money, I would not spend it on this. I would just make a smaller version. And to the left is the purple air sensor, which was also talked about a few minutes ago by Dr. Coe, which that would also cost you about $300. So another, not as expensive, but still $300. What are aerosols? It is a suspension of particles in either a liquid or a solid that's in air or another gas. The size of these aerosols can vary from about 0.01 micron to several tens of microns. The images here are just different kinds of aerosols that you could either, breathe in, or that could be found in solutions of either, or any kind of liquid solution. This is picture here showing, it's not as like advanced or as good as the image of the one to the left, but the image to the right is just what exactly you see with our naked eye. So, why use DLS? Well, humans are susceptible to particles that are smaller than about 2.5 microns. And dynamic light scattering can be used to determine the size distribution, shape, and density of these particles. As you can see on the bottom is, I'm going to call it a timeline, or a size line. Not too sure what exactly to say, but you can see 1 micron is about the size of bacteria. So a little bit bigger than that would be about 2.5, so 2.5 and smaller. Pretty susceptible to that. That's why you see viruses there. Just things that were sick, that would be harmful to breathe in. Dynamic light scattering. Here's just a rough image of what exactly is occurring when I say dynamic light scattering. We have a laser that shoots through our solution that is either, again, in a solution or it's suspended in the air. And the laser records these, it records the intensity and the time of these particles. If you can see to the image on top, which you see the distance of, you see how long it takes for the particle to actually show more peaks and to show actually what's happening. This shows that the particle is a lot larger with how long it takes for more peaks to be shown. Smaller particles are a lot quicker moving, so you see more peaks in more frequent time periods. Pearson's product moment correlation coefficient is used to determine the strength of a linear association between two variables and to extent how often the variables collide with each other. In the first image here, we see no shift, which is exactly why the image on the bottom is what we do is we get our intensity and we put them over each other on both the x and the y axis, and we plot them to see what happens, or we plot them to see what information we get out of it. As you can see, the image is originally linear without any shifts whatsoever. If we shift the image by about 100 nanoseconds, we start to see here a little bit less of a super linear picture as the one to the left, but it's still fairly linear. Not really much is changing. So the more that you're shifting it, as you see here with 200 nanoseconds, 800 nanoseconds, and 1600 nanoseconds, you begin to lose that linear image, and we start to see more of a completely scattered data points, and we're not really, it's just, it becomes completely scattered and there's nothing there to really look at. But it does tell us something important, and that is our correlation function and our delay time. So that linear scattering, what's occurring with that scattering is that the longer or the more that it's becoming less linear, it's telling us how long it's taking for the delay of the light scattering to be. So the longer the delay for the scatter to completely disappear, as you can see here and here, that the longer the decay, the bigger the particle, and the shorter the decay, the smaller the particle. This is all it's telling us is the size. And here is our autocorrelation function that we're using. It is not the standard formula for the autocorrelation function. This is because that formula would take way too much time for us to really get information. It would take way too much time for us to get the information, and we don't really have that much time, and that's the whole point of this, is to just make it more efficient. So how do we fit our autocorrelation function? Well, our A and our B are both our amplitudes, and our decay is occurring exponentially, as you can see up here. What's next that we see is our diffusion coefficient and our scattering factor. And our scattering factor and diffusion coefficient they work in tandem they work together in terms to really tell us like what we're looking for. Sorry. As we move down the formula, we get to our wavelength, and our wavelength tells us our scattering factor. And next to our wavelength is our theta angle. It's our theta angle of how the light is actually, or of the laser, the theta angle of the laser. Yeah. And all of this is mainly just to tell us what our R is, which is here, which is our particle size. So, the WIBs, the waveband integrated bioaerosol sensors. The WIBs is used more when working with pollen and flowers or spores off of mushrooms. Jack Dawson is going to be doing his capstone project using this, and his project is in conjunction with mine, as said earlier by Dr. Kelp. Okay, now we're getting into exactly what I did and what was really being done and what this whole project was about, and that was creating this mobile DLS. We have multiple different parts and multiple different components that go into this actual mobile DLS, and we started out with our Raspberry Pi, as you can see here, which is connected to our Arduino. We also have a blackout box used to get out any little noise from any noise from the outside environments to really make it more difficult for us to get a precise reading on what exactly we are trying to detect. We have, for the DLS, we have our infrared laser, our infrared light sensor, and our laser. And for the WIBs, we have our ultraviolet laser and our optical fiber, which is on top of the black box. And on the bottom of our cart, we have our spectrometer, which is connected to the UV WIBs laser, and our spectrometer, which is connected to our optical fiber, and our WIBs, which is used with the bioaerosol. So this is a picture of our pretty much completed, just need to take it outside, mobile DLS on the cart. Here is our Raspberry Pi, which we use it's the touchscreen Raspberry Pi. The Raspberry Pi is right under it. Our Arduino is connected right to it.